Welcome back. And in this series of videos, we're going to be looking at pH and Ka. So that's the equilibrium constant, but for acids. So you're going to need your notes and a calculator, and we're going to start on page 2. Okay, so we call an acid a proton donor. So it's something which has the potential to donate protons, and its base is a proton acceptor. So it has the ability to accept a proton. Now, for a chemist, a proton is simply a hydrogen ion. So it's a hydrogen atom which has lost its outer shell electron. So the acid has the ability to donate the proton, and the base has the ability to accept the proton. But this is a lot like redox, oxidation and reduction. Oxidation is the loss of electrons, reduction is the gain of electrons. In this case, an acid is a donor. It donates hydrogen ions, but it has to have somewhere to donate it to. So there must be a base present for that hydrogen ion to be accepted. Likewise, a base can only work if it has an acid to accept a proton from. So we call these conjugate acid-base pairs. In other words, this is my acid, which donates a proton, and this is the base, which accepts it. You can't have the acid on its own, you can't have the base on its own. So if we consider a couple of reactions here, I have the ammonium ion reacting with the OH negative ion. Now the ammonium ion turns in to ammonia. In other words, as it goes from the ammonium to the ammonia, it's lost a hydrogen ion. So that is an acid because it's donated a hydrogen ion. I'm going to call that one acid 1. If we look at the OH negative has turned into water. So it's gained a proton. So it's accepted a proton, therefore it is a base. And just so we don't get confused, we're going to call that base 2. But this reaction, you'll notice, is reversible. So looking at it from the other side, the ammonia, when it turns into the ammonium, picks up a hydrogen ion. So it's acting as a base. And this is acid 1, so this is base 1, because these two are what we call these conjugate acid-base pairs. Ammonium turns into ammonia, and ammonia turns back into ammonium. The OH negative is our base 2. What we've got left on this side is our water. And if we look what's happened to our water as we've gone from H2O and it's turned into OH negative, it has lost a proton. So it's donated a proton, so that is acid 2. And that's my acid-base conjugate pair. Considering the second example, ammonia and hydrochloric acid, turning into ammonium and chloride. So if we consider the ammonia first of all, the ammonia has gained a proton to become ammonium. So this would be my base 1, and the ammonium, turning back into the ammonia, would be my acid, as it has donated a proton. The HCl turns into Cl-. In other words, the HCl has donated a proton. So I'm going to call that one acid 2, and its conjugate base is the chloride ion. So that is base 2. Now in this case, because this is a strong acid, it's very good at donating protons. The equilibrium position lies well over to this side. So you get mostly ammonium and chloride. And you've seen that reaction before, and it makes white smoke of ammonium chloride. So these acid-base reactions, you can think of it as being competition for protons. So the better something is at donating a proton, the stronger the acid. Before we move on, we need to look at water. Now, water is a very unusual little molecule. It's unusual in the sense that it can act both as an acid and as a base. We say that it is amphoteric. In other words, it can both accept a proton and donate a proton. So if we consider this reaction, one of my waters is donating a proton to become an OH negative ion. The other water molecule is gaining a proton to become H3O positive. And this, generally speaking, is what's going on in all acid and base solutions. So hydrochloric acid can only act as an acid if it has somewhere to donate that proton to. Likewise, ammonia can only act as a base if it's got something which will donate it a proton. So HCl and water, HCl is my acid, and it becomes the chloride negative ion, base 1. The water, in this case, is acting as a base because it accepts a proton to become H3O positive. And this is my acid. Again, because HCl is a much stronger acid than water, the equilibrium position lies well over to that side. So most of a hydrochloric acid solution contains the H3O positive ions and the chloride ions. There's very little, if any, HCl left. If we consider now NH3, ammonia, acting as a base. So ammonia would be base 1, becoming the ammonium ion, which is actually an acid. In this case, the water is acting as an acid because it is losing a proton, it's donating a proton to the ammonium and becoming an OH negative. That is my base 2. Now, because ammonia is not a particularly strong base, this equilibrium position does not lie well over to this side. In fact, it lies over to this side. And we'll come back to strong acids and strong bases later. So here we can see good examples of water acting both as a base and as an acid, because it has the ability to gain a proton. It also has the ability to lose a proton. So when an acid dissolves in water, they separate into partially or completely into their ions. And it's this separation that determines whether or not you have a strong acid, which completely ionizes, or a weak acid, which only partially ionizes. So we quite often write our reactions like this, where we've got our acid dissociating into the hydrogen ions and leaving behind the anion. Now this technically is not correct because you have to have somewhere for those hydrogen ions to be donated to. In other words, for this to act as an acid, it needs a base to accept the proton. So more accurately, this is actually what's going on. You've got your acid, which is donating a proton to the water, which is why acids can only act as acids in an aqueous solution, or where they've got somewhere to donate that proton to. Now, this position of equilibria is very important. The amount of dissociation is different for different acids. Some acids are much better at releasing their proton, so the equilibrium position lies far over to this side. We say that they are strong acids. The stronger the acid, the weaker its conjugate base. So let's have a look at a couple of those examples. So let's look at a few examples that you may have come across before. So if we think about some acids which you use frequently, like hydrochloric acid. So in water, because this is a strong acid, it completely ionizes into the H3O positive ion and the chloride negative ion. So this is a strong acid. If we think about another acid you're familiar with, let's try sulfuric, H2SO4. And I'm just going to do the first ionization for this one. So again, we've got H3O positive and HSO4 minus. Again, notice it's not reversible because this is a strong acid, or at least the first ionization is, and this reaction will go to completion. Now, if we compare that with a weak acid, something like ethanoic acid, all organic acids are by definition weak, this reaction is highly reversible. So we get CH3COO negative, and we still get our H3O positive. But because this is a weak acid, the equilibrium position actually lies well over to this side. So you get very little of these species and you get a lot of this. Whereas in these first two cases, the reactions go pretty much to completion. There might be a little bit of reversibility, but not enough really to talk about. But if we put two of these strong acids in competition with each other, we can see which one is the stronger by which one is able to donate the proton. We're going to do that on page 3. So here we have nitric acid and sulfuric acid reacting together to form what we call a nitrating mixture. And if we look at what's going on, so this HNO3 is becoming H2NO3 positive. In other words, it's acting as a base because it's making this species H2NO3, which has accepted a proton. And this makes this its conjugate acid. So I'm going to call this acid 1. And this makes the H2SO4 an acid, and its conjugate base, HSO4, is my base 2. So you can see here my nitric acid is acting as a base. Why? Because it's accepting a proton. And it's accepting a proton because H2SO4 is a stronger acid. So here we have ethanoic acid and we have perchloric acid. So in this case, the ethanoic acid is gaining a proton. So in this case, it's acting as a base. Base 1, and here, acid 1. These are my acid-base conjugate pairs. And my chloric acid is acting as the acid, so I'm going to call that one acid 2. And it's losing a proton to become base 2. So those are my acid-base conjugate pairs, and these are my acid-base conjugate pairs. Again, please notice this is ethanoic acid, but it's acting as a base because we've paired it with a much stronger acid. Do remember, strong and weak have nothing to do with concentration. It's to do with the amount of dissociation. A strong acid will completely ionize. A weak acid will only partially ionize. And a stronger acid, for example in this first case, sulfuric acid, can force a weaker acid, such as nitric, to act as a base. We can apply the same term to bases. So the further the base dissociates, the stronger the base. So strong bases totally ionize, weak bases only partially ionize or ionize to a small extent. The other thing to remember is that the stronger the acid, the weaker its conjugate base is going to be. So the better able this species is to give up a proton, to donate a proton, the worse this is at going to be accepting that proton to go backwards. So again, if we consider hydrochloric acid, we can say that the hydrochloric acid is a strong acid. The chloride ion is a very weak base. It is very bad at accepting a proton and going back to HCl. You'll notice I haven't said anything about pH. pH is a bit of red herring when it comes to whether or not something is acting as an acid or a base. Because if you consider the nitric acid sulfuric acid example that we just looked at, if I was to measure the pH of nitric acid, it would come out as roughly 1, and the pH of the sulfuric acid would also come out usually at roughly 1. Possibly lower than that, could be 0 in both cases. But they would both have a very low pH, and yet nitric acid here is acting as a base, even though it has a pH of between 0 and 1, or maybe even a negative pH value. On the next few pages, you've got an experiment which we're hopefully going to be able to do in class, and then we're going to look at pH and what pH actually tells us about the solution. And that's for the next video. So until later, take care, stay safe. Bye-bye.